Implicit differentiation enables us to differentiate equations with mixed x and y terms, including where there's a product involving x and y. We're used to the relationship of x and y, where y is a function of x. We call this giving y explicitly in terms of x. But we have already met a number of equations, most notably those for a circle, where it's easier to have x and y mixed up on the same side of the equation. We call this giving y implicitly. Here's some examples. Well, this is what we're used to. Y equals x squared minus 4x plus 3 is an example of giving y explicitly in terms of x. Y is a function of x. But here, simple circle equation, x squared plus y squared equals 4. We call this implicit. Sometimes it's more convenient to differentiate implicit formulae as they are. To see how this is done, we're going to have a look at some of the things we know and see how we can use the chain rule to differentiate implicitly. So if we start off with y equals x squared, we know that dy dx is 2x. We've differentiated y with respect to x. We could write this as d and then in brackets x squared dx. We're differentiating x squared with respect to x, which also gives us 2x. And we can see why that's true there, because y equals x squared. So it doesn't matter whether we put y here or x squared here. So differentiating y with respect to x gives dy dx. And this is going to be an important result in a minute. So differentiating x squared with respect to x is easy. By the same token, differentiating y squared with respect to y is sort of the same thing. It's also easy. It just gives us 2y. So what we're now going to try and do is differentiate y squared with respect to x. And to do that, we're going to use the chain rule. This is what we know as the chain rule. We usually use u as a chaining variable, so we get dy dx equals dy du times du dx. We're going to make y our chaining variable. So in order to differentiate y squared with respect to x, we're going to look at d of y squared over dy. In other words, differentiate y squared with respect to y, which gives us 2y, and then dy dx, so we're using y as the chaining variable, so the result we get is just going to be 2y dy dx. And this is always the case when we're differentiating a single y term. So we differentiate a single y term, we use the chain rule, we get the derivative with respect to y, in this instance 2y, times dy dx. Okay, have a go at these yourselves. Pause the presentation, have a go. So hopefully not too bad. We know that 3x differentiated with respect to x is 3. 3y differentiated with respect to x, where we get the 3 from the dy or d3y dy and the dy dx bit. Minus x squared, simple. Minus y squared, we get the minus 2y part and that dy dx bit, and then 2 differentiates to 0. So similar sort of thing with part B. To find the gradient on this curve, well, all we do there is differentiate everything and then put the x and the y values in. And we end up with that. The dy dx is the gradient part, isn't it? So we'll let that be our m. And if we rearrange, we get m equals 1. Okay, well that's the basics. If we've got a product, it does get a bit more difficult. To do this, we need to use the product rule. Let's just quickly remind ourselves, if we're differentiating uv, a product, u times v, then the derivative of uv with respect to x is v du dx plus u dv dx. If it becomes xy, then we get that. Dx over dx is just 1. So this is what we get. And this is basically what we do. We use the product rule whenever this happens. It's easy to make mistakes when products are involved. So it's probably an idea to annotate the product in some way so that you pay attention to it. And it's important to use brackets. Particularly as with the product rule, you end up with 2 terms normally. So if you get 2 terms, you're going to want them in brackets, particularly if there's any minus signs involved. I'm going to go through a few examples because this isn't the most straightforward of topics. So example 1, we're trying to show that dy dx equals this. So the first thing we do is differentiate. We've put our little annotation in there to alert ourselves to the fact that we're going to need to worry about this product, and the minus sign there means we need to bracket it. So x squared differentiated with respect to x just gives us 2x. Y squared, hopefully you know this, 2y dy dx. And then for the product part, we put in our, well, it's xy, isn't it, which we did previously, so it's just y plus x dy dx, but note the brackets, and then that equals 0. So expand everything out, and we need to dig out the dy dx. The dy dx terms on the left hand side, factor out the dy dx, and we end up with what we're aiming at. So, bit of rearranging. Okay, another example. So we're trying to find the equation connecting x, y and dy dx and show that the coordinates of the point on the curve where dy dx equals 2 satisfy that equation. So first thing to do, annotate the product and differentiate. Well, we know dy dx is 2, so sub that straight in. Rearrange, and we can see we end up with what we hoped for. Okay, final example then. So again, we're just trying to find the equation now linking x, y and dy dx. So it's just a simple matter of differentiating. Perhaps not so simple because we've got this awkward looking term in here. So we put a p by it. Hopefully we're getting confident with these now. Same technique as before, using the product rule. We took the 4 outside, we treated the product as x times y cubed. Okay, well that's it, isn't it? We've achieved what we set out to do. We've got an equation linking x, y and dy dx. We don't need to make dy dx a subject or anything like that. We've not been asked to do that. We've achieved what we set out to do. Okay, have a go at these. Pause the presentation, have a go. If you're not sure about them, then go back over the presentation, make sure that you're comfortable with this so you're ready for the lesson on it. Okay, so the solution to the first one, And there's the solution to the second one.